Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the problem container with most water. Its syntax is double one and it is the medium problem of the lead code. Okay, so before moving on, you must have the prerequisite knowledge of two pointers because you'd be using that very well in this problem. And yes, also you need to know how the greedy approach would work, so you must have a hands-on practice on these type of concepts. Okay, so let's begin. We are given an integer array height of length n, and there are n vertical lines drawn such that the two end points of the ith line are I comma 0 and I comma height of I. If you look over this diagram, let's talk about the second bar, vertical bar. You can see the height of the vertical bar is 8, and you can see you have the coordinates as I comma 0 and I comma height of I. You can see the lower end of the bar is at the position I comma 0, where I is 1 over here for the second vertical bar. So the lower end's coordinate is 1 comma 0, and the upper end coordinate would be I comma height of I, which is the height of the vertical bar. Okay, so if you talk about the second vertical bar, the height of the coordinates are for the lower end as 1 comma 0 and for the upper end as 1 comma 8. Okay, and we need to find two lines that together with the x-axis form a container such that the container contains the most water. Return the maximum amount of water that a container can store. Okay, notice that you may not slant the container. Okay, so let's look over the constraints. N is maximum around 10 raised to the power 5. So we would be looking for the O of n solution or O of n log n type of solution in this problem. So, but probably we'd be looking for O of n solution that would work for the best in this problem. Okay, use the help of the concepts called two pointers. Okay, so let's understand this problem in detail. So the very same diagram that I have drawn over here. So you need to find two vertical lines, like over this position. This is the one of the vertical line, and this is the second vertical line, and this is you need to draw a rectangle such that this will be the length of the rectangle and this will be the width of the rectangle, and you need to maximize the area contained by this rectangle which contains the water, which is actually L into W. Okay, so let's talk about all these things in mathematical terms. So what we need to do is, like, we need to find a container that contains most water such that the rectangle that is being formed, the area of the rectangle that contains the water should be maximized. Suppose L is the length of the rectangle and W is the width of the rectangle. So if you talk about the area, which is actually L into W, so you need to maximize this area, that is, you need to maximize the L as well as you need to maximize the W. Okay, now you are unaware about that how much you need to maximize either of the parameters. So one of the best cases is to consider one, either L or W as fixed. So what I will do is, like, I will fix this length. Okay, so let's begin. So you need to maximize L and W. So let's just start with the maximum L. So I will keep L over here, and okay, yeah, so one end of this length, rectangle length, would be over here with the very starting position, and the other end would be at the end position of this array. Okay, now you need to find the container that will contain a most water, and the container that will be formed containing water will be a rectangle, right? So we will start with the maximum length, that is L will be starting with 0 and R will be starting with the n minus 1. Okay, so the length formed would be the maximum. Now we need to maximize the second parameter, which is W, such that the overall area that will contain the water will be maximized. Okay, so now you can see the water that will be contained over this entire position from L to R. So you need to know the minimum width would be min of height that would be present over L and R, right? That would be the container that would contain the most water, right? So what I will do is, like, if you are at this L and this R, your current area would be, let's denote the current area as A dash, would be the length would be R minus L. If you consider over here, L is 0 and R would be, if you find out the total number of vertical bars, it would come out to be 5. So R would be coming out to be, and sorry, total number of vertical bars is 9, so R would be coming out to be 8. Denote that we are using a zero based indexing. So the max length would be R minus L into what is the width. If you take the two vertical bars as this array of 0 and array of R, then it would be min of h of L, where h denotes the heat array, min of h of L and h of R. That would be our minimum possible, like maximum possible width. Okay, so we need to multiply it with the length as well as this maximum possible width. Okay, now the very tricky case is like how do we move further. Now one thing also that should be noticeable over here is that since we need to maximize the area, the very key concept that we are going to use is fixing one of the parameters, either L or W. Here we are, for the convenience, we are using the length parameter. Like we would be starting with the maximum possible length, fixing L as 0 and R as the end of the position. Now if you are able to fix these two positions, here we goes for the maximum length. Now we need to focus over the max W, right? So we need to find out the maximum width such that we are able to form a rectangle and the container will contain the most water in that rectangle, right? So that would be min of HL comma HR, right? So that is the term that we are using. Now since like the area can be like the max area that can also come from the like some random L and R, so we need to move the pointers L and R such that L and R should never overlap. Like L must always be strictly less than R, and we need to move the pointers till that. Now you can see the max area comes when L is 1 and R is end of this array. Okay, so we need to move some pointers either to the forward for L and backward for R. So how we are going to do that? Now since if you look at the terms that is coming in the width, so this will help us to move L pointer and R pointer respectively. Now consider HL is strictly less than H of R. Now when HL is strictly less than H of R, and since we need to maximize the width, we will always discard HL because that would not contribute in maximum width. So we need to search for the maximum width, right? Since HR is strictly greater than H of L, we would discard H of L such that we may get some maximum width that would help us in maximizing the area. Okay, so whenever h of L is strictly less than h of R, we would do L plus plus in search for a maximum h of L, so that the area A dash would be maximized. Okay, and what about when h of L is strictly greater than h of R? So since h of L is strictly greater than h of R, we would be looking to maximize the area. In that case, we would discard the height discard the minimum height, that is h of R. So in that case we would do R minus minus. Now what about when h of L is exactly equal to h of R? In that case it doesn't matter whether you increment L or decrement R, you can do any of the things, right? So you can do either R minus minus or L plus plus. So let me write down clearly, it all depends upon you, right? So so in this case, when you can see h of L is 1 and h of R is some greater value called 7, so you need to increment L, so L comes over here. So in that case R minus L would come out to be some length of the container, and heat of the maximum possible width would be min of h of L and h of R, which would be min of 7,8, which is coming out to be 7, and R is 8 and L is 1. So 8 minus 1 is 7, 7 into 7 is 49. and this is the maximum possible area. If you look out the answers, it is 49. So let's look out for the code how we can implement all that efficiently. Okay, so I will take answer as 0 and L as 0 as well as R as the end position of this array, and I will go through L less than R, strictly less than R. Note that we are starting with the maximum possible length. So every time we would try to maximize our answer. So max of answer and the length, which is R minus L, and the max possible width is min of H of L and H of R. And if heat of L is strictly less than heat of R, we would increment L in search for a maximum possible width that we can have, otherwise R minus minus, and finally we would return the answer. Okay, so you know the time complexity is O of n because we are going for every element exactly once, and space complexity is O of 1. So if you guys have still any doubts, you can reach out to us through the comment section of the video, and thank you for watching this video.